Hello everyone, today I'm going to introduce our paper, Minimally Supervised Structure-Rich Text Categorization while Learning on Text-Rich Networks. This is a joint work done by Xian and Jiawei from UIUC, Chenwei and Luna from Amazon, and Jingbo from UCSD. My name is Xian and I will be presenting today. Now let's talk about the motivation of this project. Well, text categorization is quite essential for web content analysis and could benefit various downstream applications. We notice that text collected from the web is often structure-rich, or in other words, accompanied with metadata. Meanwhile, we found that most existing approach relies on a large amount of training data. This is very costly, especially when the number of categories is large, or when handling evolving categories. Well, in this work, different from most supervised approach, our goal is to categorize structure-rich text documents given only a handful of seed examples per categories, and in our experiments, no more than 3 hand-labeled documents per category. Formally, our problem can be defined as follows. Given a set of documents, their accompanied metadata, a set of labels, and a few labeled documents per category, we aim to learn a classifier which can assign correct labels to incoming documents. The first step in our framework is to organize the structure-rich text corpus into a text-rich network. As you can see in the figure here, a text-rich network is a heterogeneous network with various node types and accompanied by abundant raw text information. For the nodes in the network, we have documents. We have document attributes such as authors and publishers of books, and those two are given as input to our framework. In addition to those, we also perform label surface name matching, as the occurrence of a label surface name could serve as a weak indication of document category. And we also mine high-quality phrases to explicitly model textual similarities between documents. For the edges in the network, they capture document and attribute relations. Besides the network structure, the document nodes are also associated with their raw text content, and this is also why we call it a text-rich network. There are several advantages of using a text-rich network to represent a corpus. It naturally incorporates heterogeneous data sources, captures their relations and interactions, and moreover, it also enables network-based analysis of the corpus, for example, ranking or clustering in the network. There are 2 major challenges in modeling text-rich networks. The first one is how do we combine text and network together? So if you just put a deep text model and a deep network model together, it may be overly complicated and not suitable for our minimal supervision setting. And the second challenge is how do we handle the so-called mixed signal from the text-rich network structure. So basically, the network is not constructed in a label-indicated way. And we identify 2 key properties here. The first one is called so-called weak homophily, which means if 2 nodes are connected by an edge, it does not necessarily mean that those 2 nodes are from the same category. And the second one is imperfect linkage, which means nodes and edges might be wrong or uninteresting for our classification task. To address the challenges I just mentioned and to effectively learn a classifier with minimal supervision, we propose a novel framework and we call it Learning on Text-Rich Networks, or in short LTRN. Here is a sketch of our framework. Overall, this is a pseudo-labeling framework, which means that we assign pseudo-labels to unlabeled examples, and the model gets improved over iterations by leveraging those generated pseudo-labels in the training process. We also have 2 main components, a text analysis module and a network learning module. The text analysis module handles the raw text content from the text-rich network, and we use it for document classification and embedding. So this part is important because the text is still the main source for our categorization task. Now, as for the network learning module, our objective is to handle the text-rich network structure and also do classification based on that structure. For this part, we want to design a class discriminative and scalable graph neural network model to handle it. Now, given the two separate modules, we put them together through joint training and let them mutually enhance each other. We have two parts in this joint training. First one is co-training, which means the predictions from one module is used to improve the other module. And we also have feature sharing to share the up-to-date document features from the text module to the network module so that the GNN model can effectively leverage those up-to-date features. Now, after the framework is fully trained, we use the text analysis module as our final model to handle the incoming new documents for the classification task. Now let's take a look at the components in more details. For the text analysis module, we use a BERT model here. We first run language model fine-tuning on the unlabeled documents, and then we use a model for document classification and document embedding. For document classification, it's quite standard. We just add one linear layer after the CLS token and use it for classification. And for the embedding, we actually have two different strategies here. The first one is applied before the model is fine-tuned on any real or pseudo label. We use the average token embedding except CLS and separation token. We use this method because we find it more effective in our real-world experiments compared to using CLS token embedding for document embedding. And the second strategy for document embedding is just to use CLS token embedding. So this one is more effective once the model is actually fine-tuned on some labels through later iterations of the whole framework. For the network learning module, we use a graph neural network model. Now, instead of just applying an existing graph neural network model, we want to design a GNN that can handle the imperfect text-rich network structure. As we mentioned earlier, the network structure has weak homophily and imperfect linkage. So we want the model to handle that. And in the meantime, we also want the model to be scalable. So the general workflow of the GNN looks like this. For each node in the network, we first do a feature transformation on the node features. And then we apply an aggregation function on the node according to the network structure to aggregate features from its neighboring nodes. As we can see here, the aggregation function here is actually a more interesting part in the GNN structure. For this part, we have two different strategies. The first strategy is a personalized PageRank-based neighborhood sampling strategy. So instead of just taking all the first hop neighbor of each node or doing random sampling of the neighbors, we actually use personalized PageRank to retrieve the most important neighboring nodes for each node in the network. And we can see here, formally, for each node in the network, we sample its top k neighbors according to their personalized PageRank score with respect to that node in the network. The second strategy is an attention-based aggregation strategy. Now, after we have retrieved top neighbors according to the PageRank score, we apply an attention-based aggregation to let the model figure out which neighbors are actually more useful. Now we have introduced two main modules of our framework. Let's talk about the joint training that put two modules together. For this part, we also have two different strategies. The first one is co-training, which pulls the pseudo labels generated from each module together. As you can see here, in each iteration of the algorithm, we take the confident predictions from both modules and put them together and use them as the pseudo label set as the input to the next iteration of the model. The second strategy is feature sharing. Because the GNN model requires node feature as input, now instead of just using fixed document feature for the GNN, at the end of each algorithm iteration, we actually redo the document embedding with the BERT module and use them as a new input to the GNN, so that the GNN model will always get the most up-to-date document features. Now let's take a look at the experiments. For the experiments, we have two datasets. The first dataset is an Amazon product categorization dataset. It is collected by us. It has 683 categories. The number of categories is much larger than most datasets used in related works. It is a very challenging dataset to benchmark the minimally supervised setting. For this dataset, the text part includes product title, bullet point, and description, And for the attributes, we have brand and manufacturer of the products. The second dataset is a book dataset. It has 8 categories of different book genres. For the text part, we have book title and description. And for the attribute part, we have author and publisher of the books. For all the datasets, we use 3 seed examples per category as labeled examples. And meanwhile, our experiment setting is inductive, which means that the test documents are not observed during training. Here's the result from our main experiments. We compare our model to various baseline methods. The baseline methods can largely be grouped into text-based methods and network-based methods. As you can see in the table here, our model consistently outperformed all the baseline methods on both datasets. And also note that on the challenging Amazon product categorization dataset with hundreds of categories, our model achieved less than 2% F1 score difference compared to the supervised BERT model with 20 times more training data. We also show multiple case studies and ablation studies. In the case study here, we try to see how the network and text modules of our framework mutually enhance each other through the joint training process. In the figure here, the x-axis represents different categories on 2 datasets, and the bars in the figures show the performance of the GN model from the network module and the BERT model from the text module. As you can see, at the first iteration, the 2 models have substantial performance difference across different categories. And if you look at the last iteration on both datasets, both modules have improved their performance, and their performance difference has been much smaller than compared to the first iteration. In the ablation study here, we show 2 model variants. In the first model variant, we remove the feature sharing mechanism from our model to see if that mechanism actually helped the joint training process. In the second model ablation, we replace the proposed GN architecture with a graph stage model, so that we can compare our proposed personalized PageRank-based neighborhood sampling and an attention-based aggregation to a random neighborhood sampling and aggregation scheme. As you can see in the table down here, both model variants have inferior performance compared to our joint model, which kind of verifies the effectiveness of our proposed model. In the final experiment here, we change the number of labeled documents and see how that impacts the model performance. As you can see in the figure down here, generally when the number of seed documents increase, the model performance increase. And you can also see the model variation through the error bars in the figures. You can see that although model does have some variation, it does not matter much. Now, wrapping things up, in this project, we provided a text-rich network perspective to combine text and metadata for minimally supervised text categorization. We proposed a joint learning framework with a text analysis module and the network learning module, and both modules are data-driven. We did experiments on 2 datasets, including one Amazon product categorization dataset collected by us with around 700 categories, which is quite challenging. We achieved significant performance gain compared to all the baseline methods, and on that Amazon product categorization dataset, we are nearing the performance of a supervised BERT model. For more details of the project, please take a look at our paper. Thank you for listening.